We're going to walk through some non-negative matrix factorization. I really like this stuff. I think it's pretty awesome that we can do this. Yeah, I think it's super powerful. It basically gets the question of, well, what if I don't know what my sources look like? Is there anything that I can do, right? Because all of the stuff that we've been talking about up till now, the sort of forward mixing models, you have to know, or at least have an idea of what your sources look like, so that you can put them into your into the model and mix them in whatever way you're going to use to mix them, either Monte Carlo or some optimization routine, to sort of match what the measurement that you've observed. But again, what if you don't know what those sources are? Is there anything that you can do, or are you stuck? And so non-negative matrix factorization sort of addresses that question. So in our course schedule, again, I've mentioned this already, we're in the home stretch, folks. We'll talk about the theory behind non-negative matrix factorization, and how that can be used to identify and characterize unknown sediment sources. We'll talk about how to use breakpoint analysis to determine the optimum factorization rank, and what is an optimum factorization rank. And then we'll dive into DZnmf to apply some of this. So our outline for today, there it is. We're heading into this red section there. So the fundamental question here is, if I don't know what these colored distributions up at the top with these yellow, red, purple, all these guys look like, and all I know are these black filled distributions at the bottom, can I get back to not only what these guys look like up here, but how these mix into any one of these? So the weighting functions that mix these sources into all of these sink samples. So there's some caveats that we need to acknowledge going in. So one of the things that we need to know, or that we need in order to apply this method, is that the number of our sinks has to be much larger than the number of our sources. And my sort of rule of thumb is about 2 to 3 times as many sinks as you expect to find sources. So if you've got 20 sink samples, you're probably not going to find more than, in those samples, you're probably not going to be able to identify more than between 7 to 10 sources, right? It's just your data limited. But by, so the inverse of that is that if I've got lots of data in my, lots of sink samples, lots of basin samples, then that gives this method power. It's sort of, the method is most powerful when you have lots and lots of data to throw at it. It's also most powerful when those sink samples are fairly dissimilar, right? So if all of your sink samples look the same, essentially, or if they're very similar, think low KS values or high cross-correlation coefficients. If they're all really similar, then you're not going to be able to factorize those very successfully into their constituent sources. As we've harped on throughout this short course, our sinks need to be well characterized, and typically that just means a large N, right? So lots of grains. If you've got a bunch of samples with N equals 70, again, you're not going to be able to successfully factorize them as well as you could if you had the same number of samples with N equals 300 or 400. And then the last one here is that recycling is not always obvious. So a few caveats. Just want to make sure that those are clear at the outset before we dive into this. And we've mentioned this already. These PDPs or KDEs can be characterized as can be discretized and therefore characterized as matrices. We can treat them as evenly spaced time series, and we can apply a lot of the methods that people have developed for signal analysis, which is actually, NMF is one of those methods that that people have applied for signal analysis, and we can apply it here to PDPs or KDEs. At one point, someone had asked whether or not, or which of the various metrics that I prefer. I think one of the reasons, or basically the only reason that I would prefer one over the other, is that NMF cannot be applied to CDFs. So we've tried using NMF to factorize CDFs, and we were unsuccessful, at least in our sort of preliminary trials. And obviously they work for PDPs and KDEs, but that means that you're limited to the comparison metrics, including cross-correlation, similarity, and likeness. Or if you want to sum these guys up, you can apply the KS or Kuiper statistics to cumulative sums of these guys. But fundamentally, you're limited to relative probability distribution-based metrics when you're dealing with non-negative matrix factorization, particularly. So given that these are matrices, right? We can think of V, which would be our matrix of sync samples. So that'd be sync 1, 2, 3, 4, 5, and 6, where each of these, each row would be the probability at a particular age, and could extend from, for example, 0 to 4,000. So that matrix can be characterized as a matrix multiplication function of W, which would be some basis function, which would be our sources. In this case, I've sort of arbitrarily said, well, we've got 3 sources here. So source 1, 2, 3. Also, relative probabilities in the rows, and and going from 0 to 4,000 or whatever, and weighting functions. So H, so weight 1, 2, 3, plus potentially some uncertainty, some misfit there, right? So V equals WH plus E, essentially, where if you're looking for the probability of that particular cell, the value that should be in that cell in your matrix or in the Excel file, it'll be essentially the product of that times that. So you can see that down here. So it'd be W11 times H12, W12 times H22, W13 times H32, right? Same thing goes for that cell. It would be the product of that times that. And in summary, we can say that sync 2, for example, is the product of W times that weighting for 2. Sync 4 would be the product of W times the weighting for 4. And the nice thing there is that gives us, again, we can sort of we can play the iterative recombination game where this basis function plus these weightings that we have to be able to match all of our sync values here, our sync matrices here, or you have to start over and try again. So we can essentially go through and, starting from a random starting point in W and H, we can iteratively update those guys and try to minimize the misfit, try to minimize that E value, so which would be the misfit between V and WH. So the whole idea here is to minimize that misfit, which is E in this equation, but realizing that that it may be non-convex, right? So if we're trying to minimize E, we're trying to get as low as possible down here, and we had a perfectly convex function, we would be able to get to essentially a global minimum, which would be down here. But NMF is by nature a non-convex problem, and so there may be local minima. And so depending on our starting location, sort of in this space, we may wind up at a local minimum rather than what would be the global minimum down here. And so you might say, well, what do we do about that? The solution, at least that we've implemented in DZnmf, is multiple runs. Because that starting point is random, the idea is that if we're sort of randomly sampling the starting space here, eventually one of those is going to give us our minimum value, and then we simply select the run that gives us the lowest final residual as the one that we prefer. In terms of an idealized example, well, actually, before I go there, so that's sort of an introduction to the method, and I want to pause for just a minute and make sure that people are still with me, and also give my co-hosts a chance to chime in if they've got anything to add at this point.
I think that was pretty clear. I don't know that I could add much at this point.
Was that a question? Okay, if not, let's press on. So we'll look next at an idealized sample. And in this case, we had a number of known sources, right? So Kurt and I came up with 10 known sources. And these are sources, actually, these are the same ones that I used for the MDS example. And in this case, we're representing those sources as KDEs with a 20 million year bandwidth. We took those sources and mixed them randomly into 40 sync samples. And we kept track of the mixing weights. And obviously, we know what those sources look like. And so then we took those, we set the 10 sources aside. We took the 40 samples and we fed that into the NMF algorithm. And what we wound up factorizing out, so you can see the inputs here, so the 10 sources, again, that the algorithm never saw, because all we fed the algorithm was the basin samples that were mixed from these. But nevertheless, the sources that we know are sort of the original sources are in black, and then what we factorized out of those 40 mixed samples are there sort of mirrored in white. And what we found is that essentially we were able to fully recover the distributions using this NMF routine. So in terms of recovering our basis function, the distribution of ages, W, we were able to fully recover those. The comparison, if you want to compare the sort of quantitatively compare each of these sources to their factorized equivalents, we're getting v-values basically of 0, so 0.006. We're getting cross-correlation coefficients of 1, or rounding to 1, so 0.996. Essentially, these, for all intents and purposes, these are identical, and with the caveat, with the understanding that this is a fully synthetic data set, it's pretty remarkable nevertheless. I was sort of floored when I saw this. So again, just making the point that all that the NMF algorithm ever saw was these 40 sync samples. It never saw these the 10 original sources, and yet we were able to get back basically what those sources look like. Yeah, cross-correlation and Kuiper indicate nearly perfect matches. But not only that, and again, this floored me when I saw it. we were able to get back the weighting functions. So we had kept track of the weighting functions as we mixed those 10 sources into the 40 samples. And then, you know, we took the weighting function that the results gave us, that after factorization, so that H matrix. And if we plot them against each other, so the input weighting functions down here and the factorized weighting functions here, obviously they string out just about perfectly along a one-to-one line with a cross correlation coefficient of or a Pearson's coefficient of determination of about 0.95. So pretty cool. It means that not only can we characterize the age distribution, we can say something about the way that those source samples were mixed into our sinks, and say that with a fairly high degree of confidence. And again, I want to stop there because I'm going to move on to talking about determining the number of sources. But before I do, any thoughts or questions about that idealized sample?
Hey, Joel, one thing that I wanted to point out, based on how I think I understand this stuff, and you'd be able to comment on this better, but if you go back to your last slide of, randomized the weighting functions that you assigned, it's my understanding that this method does particularly well when you've got some samples that are almost 100% comprised of some of the sources. So if there's some of your sink samples that look a lot like what the potential sources are, these unmixing approaches do a pretty good job of being able to settle on the solution, but that things become a little bit less identifiable as you start to have a lot more mixing coefficients or a lot more well-mixed samples in the middle of this. And I think that's sort of what you pointed out earlier, that you need a little bit of diversity in how different the samples are. But I think that comes into play specifically in sort of where how far out on the axis we are in this function, right? It's easier to fit this line if something is at a really extreme X value than if everything is just sort of mixed around in the middle.
Yeah, I think that's definitely true. I think what we see being particularly, so again, having a wide range of a diversity among your sink samples definitely helps. We see that if all of your sink samples look quite similar to one another, you can have trouble reproducing or extracting the age distributions and the mixing weights. So I think that's accurate. And I've got some slides at the end of this presentation that people can look at, or I can talk to maybe later on if people have more specific questions or if people want me to revisit that. The other thing that again, I would agree with what you're saying, and I think another implication and another way that we see that in the data and in the data analysis is that it is difficult to identify recycling. So if you've got a well-mixed source, it's often difficult to unmix that source. I think of it in terms of, it's difficult maybe to see past a particular source in the geologic record. So if you've got sort of, again, I think of it in terms of like a mountain range or a couple mountain ranges up there that are feeding sediment into a basin that you're then recycling that basin into a second basin. NMF might be able to get you back to that first basin, but it won't necessarily be able to get you back to what the mountain ranges look like unless you have some independent estimate of maybe one of those mountain ranges, the age distribution from that mountain range. So all of that to say that recycling can be an issue, and I think it comes back exactly to what you're saying, that if your sources are well mixed and you don't have a good proxy for any of the N members, you might run into trouble. Other thoughts or comments sort of along these lines, because I'm gonna move on to thinking about the factorization rank. So Mark asks, what if you have some idea of the source samples, but not all of them? I guess there are a couple ways that you could treat that, right? You could factorize your samples and say, well, which of these samples, which of the factorized sources match the one that I think is out there, and maybe can I pull that out and then look at the other ones? Or you could stick that particular source into the mix and factorize the data set with that in the mix, with the intent that that then becomes one of your N member sources. So probably, if you stick that in, the NMF algorithm will identify that as one N member and will pull that out of side. And you'll be left with trying to match the rest of your data with sources that you may not have independent evidence, you may not have characterized independently.
I have another sort of weird suggestion, although I'm curious to hear what Glenn has to say too, for Mark's particular example. You could do the forward approach that sort of Kurt and I used, and then look at the residual between your model and your observation as a way to try to characterize what is missing from your child, and then interpret that residual in sort of the context of the paleogeography as you can understand it from your, independent information.
Yeah, it's an interesting idea.
Yeah, my comment was going to be similar. I think this goes back to what has been said already, that these modeling frameworks need to be applied to a geological context that you understand well. So a really important step of this, and I'm sure Joel will get to it here, is you will get these N members that are derived from the data, but then how do you interpret those? So basically going and comparing those with what you think are potential sources is a really important step. And it might turn out that you had something that you didn't realize was a source, kind of getting to your question, and that might help you think more critically about that and maybe come up with a more nuanced interpretation.
I'll just build on what all three of you guys said. Mark really highlights an excellent point that these are complementary methods in terms of building hypotheses and hypothesis testing. Forward and inverse approaches, whether you know the sources or you only know some of the sources. Yeah, that highlights a great point that these are indeed complementary methods.
So let's see. Yeah, so one of the things that I've sort of swept under the rug so far, dirty little secret, is that so far everything that I've told you assumes that we know how many sources there are, or the factorization rank, right? So I know that there are 10 sources in this 40 sample data set because I mixed it and I did it myself. But if I just got 40 basin samples, there'd be no reason that I would necessarily know how many sources to factorize that into. And that particular unknown, so how many sources I'm going to factorize my data set into, or the factorization rank, is one of the key criteria for success, right? So just as an example, imagine if I hadn't known that there were 10 sources and I tried to factorize this into 9, not only would I miss one of my sources, but some of my other sources would have to sort of take up the slack, so to speak, and match my data with age populations that aren't in fact there. And the same thing applies for the weighting. Some of the weightings would have to take up the slack, so to speak, and make up for those age populations that aren't there. All right, so how do you determine the number of sources? I spent a lot of time trying to figure this out. And the best solution that I came up with was essentially you factorize across a huge range of sources, or a huge range of number of sources, in terms of you start from basically n equals 2, so NMF rank equals 2, and you take it out to a lot. I usually take it out to about 2/3 of the total number of basin samples that I have. Again, so if I've got 30 samples, I will run this NMF rank optimization sort of function from 2 to 20. And the idea is that I want to see when the final residual, or that value E, right, that I pointed out in the previous slides, when that goes from decreasing fairly rapidly, like here, to decreasing more slowly, like there. And essentially what I do is, once I've got these points, I do a linear or a segmented linear fit to that plot, and I'll go back and hopefully this will run again. So segmented linear fit, and each of those linear fits gives me a sum of squared residuals that plots over here. So that would be the sum of squared residuals for the initial red line. When my breakpoint is at 2, or sorry, when my breakpoint is at 3, that would be the sum of squared residuals for that segmented linear regression. When the breakpoint is at 4, that would be the sum of squared residuals for that breakpoint, etc. And when you get 2 linear fits that fit well, you minimize the sum of squared residuals, and that in fact correlates well with the optimal number of sources. And we see this both in synthetic data sets where we know the number of optimal sources, and we also see it in sort of independently determined data sets. So for example, in the book Cliffs, we actually did a forward model where we threw a bunch of sources at our sink samples and consistently found that one of the sources was not included in that forward model. And so it seemed like we best modeled those samples, the book Cliff samples, with 5 sources. And then we came and did this NMF sort of breakpoint analysis to our sink samples, and found that in fact the empirically determined optimum rank was in fact 5 as well. And so that provided sort of the stepping stone between fully constrained synthetic data where we know what we put in and we can reproduce that, and fully unconstrained empirical data where we don't know anything. And we had sort of this nice stepping stone in the book Cliffs that was sort of halfway there, and we were able to make that leap to the sort of partially constrained data. And so we feel like we can then take a further step to the totally unconstrained data. So I should say there are some caveats here, and particularly the breakpoint is dependent on the ranks tested. And so the recommendation there is test to a higher rank. You can imagine in the sample that I've put up on the screen here, if we had only tested out to 6, we might get a different total number of or optimum number of sources than we did given that we tested out to 10, for example. So the breakpoint is certainly dependent on the ranks tested. Test to a higher rank if there's any doubt. So let's see, we've got how much time left? About 15 minutes? No, how much time do we have left? Yeah, we do have about 15 minutes left. So I want to introduce you guys to DZnmf really quickly, and hopefully run through a couple of examples with you in these last few minutes that we have together. So I'm going to open DZnmf. hopefully. Seems to be taking a while. If you're following along, I would recommend that you do the same, and we can sort of work through some of these together. My. My computer is struggling today. All right, here we go. Cool. So there are a couple things that I want to try. So starting here, we're going to go to the load data, and as with many of our applications, it brings up a browser here, and we'll select. Let's do this guy. So select application 5 syncs 1 through 10 from 5 sources. We'll open that. And it should populate the samples over here in the loaded samples. So we'll activate all of those, and you'll see it move to this window, and it'll also activate these guys here. And I'm going to give an example of where we're maybe trying to calculate too many sources off of too few sync samples. So I'm going to try and calculate, so factorize this to 5 sources, and we'll see sort of what results we get here. So just run this NMF. And got the nice weight bar there, of course. So there are the results. And here are what we know are those 5 sources, right? And so there are a few issues here, particularly, look at comparison between this sample here, the second from the bottom of the input sources of our known sources, and either this bottommost sample or that sample. Clearly, we're not getting very good separation of our source age distribution based on factorization of these sources. So let's deactivate all those guys. Don't clear anything, but we're going to go back to the load data function. So bring up that window again. We're going to navigate to this other data set, and we're actually going to merge these two. So select the application 5 syncs A through J from 5 sources, and we'll open that. And you'll see it appends it to the bottom of the loaded samples. So we've got now 1 through 10 that we initially loaded, and then A through J that we just loaded now. And we'll activate all of those. Obviously, we have more samples here now, and we can run NMF again. Again, still sticking with 5 samples. And it ran a lot quicker, actually. It's done already. And let's pull this over here quickly just to, we'll just do a visual comparison of these data sets. So we've got that big spike there. That's pretty good. We've got the Archean peak there with a little bit of Phanerozoic noise on the front. That's pretty good. We've got that Grenville peak. The Grenville peak in our NMF has a little bit of Phanerozoic noise there, but not too bad. We've got our sort of Mesoproterozoic peak with again with a fairly significant Phanerozoic population, and then we've got that really broad sort of Neoproterozoic to Phanerozoic population there as well. So the take home here is that more samples is better. You're going to get a better result if you can throw more data at this method, and it can handle the data. It's sort of where its power lies, right? Let's see. Trying to think what else I want to cover here. on. I guess let me try a factorization to determine the optimum number of sources here. So we can go to DZnmf and we will load up you know, actually, why don't we load up let's load, well, let's clear all first, and then let's load the Garrels and Pecha Grand Canyon. So this is where we started the talk today. Actually, this is where Kurt started our short course today. Seems like a good place to end as well. These are the that data set from the Grand Canyon that Kurt presented to us earlier in the short course. And we're going to determine the optimum number of samples here. And I'm going to take this down to see if we can't get away with maybe 15, 14, try 14. We should do more, but it'll take a while to run that. So let's run 14, and this may take a while. What you'll see if you're running this on your computer is you'll see a number of sources or a number of weight bars sort of pop up, and they'll start to fairly quickly fill and then disappear, and the next rank will pop up. And this is it running through each of those ranks from 2 to 14 and calculating the best fit and the residuals based on that, so that it can calculate the optimum rank. And while it's doing that, I'm going to ask, again, this is probably going to take about 10 minutes or so. So maybe this is a good time to open it up to the floor and see if you guys have any questions based on this or based on the things from the from earlier today.
For starters, thank you very much for the excellent course, guys. So if I have, say, about 200 samples from a basin that's evolved from the Triassic through the Jurassic, and I'm hoping, and I know some of the basement samples that are sourcing it, and I want to learn about sort of the tectonic history of the basin through time using, I guess, theoretical sources using this method. How long is that going to take to calculate?
Well, I wouldn't run it out to 200. I'm not even sure if I would run it out to whatever, like 100 and some. I would probably, you know, to try to determine an optimum rank based on that, I would maybe run it out to 50, right? So there's diminishing returns eventually. You could maybe push it to 75. It's going to take a long time to calculate 75, though. You know, on the order of, goodness, half a day or a day. I mean, quite honestly, I would say pick a high number. I would say pick a number that's 2 or 3 times what you realistically expect to be the number of sources, and just expect it to take a long time to crunch through that. And
Joel,
again,
do you want to say something about what happens when it doesn't find a solution? So when the green bar goes all the way across and it doesn't reach your threshold.
Yeah, so you can,
that might build on what you just asked.
yeah. So maybe, so I'm not gonna have time to show this or to demo this, but if you set if the green bar goes all the way across, it's essentially running this many iterations. So in this case, running out to as many as 10,000 iterations. But if it gets all the way across there and it hasn't converged down to a final residual of 1 to the minus 8, or an incremental improvement between iterations of 2 to the minus 16, or 10 to the minus 16, it's going to ask you, it's basically going to tell you that the factorization did not converge before the maximum number of iterations was reached. And it's going to ask, do you want to run multiple iterations? And if you say yes, it's going to ask you, well, how many iterations would you like to run? 50 is a good number. I would say more is better, right? And when you hit OK, it's going to then do that factorization that you just set up. It's going to do that 50 times, and it's just going to run through 50 times, looking for the lowest final residual. And so that's where I mentioned, given the non-convex nature of NMF, sort of running through it multiple times to try to use the random initialization point to maximize your chance of finding the global minimum. That's essentially that approach. Once it's run through those 50 factorizations, again, if it hasn't found if it hasn't converged by that time, it'll go through this again, and you can say, yes, I want to run more iterations, or you can say no. And what it'll report at that point is the lowest final residual that it has found up to that point. And so you can take that with whatever grain of salt you decide to take it. My recommendation would be to take it with a fairly large grain of salt at that point, because you weren't able to get it to converge. But it also means that you can leverage that ability to sort of maximize the chance that you're finding a global minimum. And what I mean by that is that you can sort of artificially set your final residual or your incremental improvement to really, really low values, 1 times 10 to the minus 100. Incremental improvement, similar, 1 times 10 to the minus 100, and force it to go through this repeated iteration process in order to leverage the possibility of starting at a random initialization point to get as close as possible to a global minimum. Yeah, was that sort of where you're headed, Kurt?
Yep.
Okay.
It's just more caveats, just because it's spitting out an answer doesn't mean that, you always got to verify with geology, and then also what does the model result mean, kind of mantra today.
So we are about to finish this up. I am just, I'm actually going to have you guys tell me how many sources we've got as soon as this finishes. In the meantime, any other question? Starting to take a while here. As you can tell, it's starting to crunch through larger and larger data sets, and so going slower and slower. Hence, Mark, again, set it up on a separate computer and let it run, and it'll do its thing. It'll just take probably quite a while.
I'll just throw in some comments. So the few case studies where I've used this approach, I found that as you know, even if you have a lot of samples, your ability to interpret the meaning of these N members at some point tails off. And in the data sets I've worked with, I've become increasingly concerned about noise coming into the data set, either through just you know, incomplete sampling or analytical noise or whatever. And so, you know, there's of course the sort of rank. You can compare the sort of that linear approach that Joel described, and I think that's a really great starting point. But ultimately, there's going to be some interpretation involved with this, and I think that's okay. But it's just something to be aware of, that you've got to be prepared to interpret these results and put them into a geological context that makes sense.
Apparently I did one too many samples here. I should have gone for 13. Oops. You guys shouldn't be seeing this yet. Yeah, so I'm going to end polling here. And I'll actually relaunch that in just a minute. Okay, here we go. So the question for you guys is, you've sort of seen this already, but that's fine. Relaunch the polling. How many sources? Clearly. Again, it would be great if this hadn't popped up with the number of sources in the DZnmf window, and you guys could just interpret the figure 1 and 2 that you can see there. But nevertheless. Couple more seconds here, just for the fun of it, put an answer in there, and I'll end the polling here in about 5 seconds. All right, let's end that and share the results. And y'all are excellent, ready to take on the world with NMF.